In this video, we'll talk about mechanical and electrical vibrations, the main physical applications of the second-order linear equations. So we started this chapter talking about physical situations that gave rise to these differential equations. There were two main examples here, the idea of the mass on a spring and the idea of electrical circuits or RLC circuits. And both of these, if we write them out, give rise to equations that look very similar. For the mass on a spring, mass times second derivative plus drag coefficient or damping coefficient times the first derivative plus spring constant times the function equals 0 or some function depending on if there's extra forces going on. And for circuits, we get a similar setup. The inductance, second derivative of the charge, plus the resistance times the first derivative, plus 1 over the capacitance times the charge itself, equals either 0 or some voltage applied to the circuit. So in either case here, we're down to a second order constant coefficient equation. So we're left with something like A times y double prime plus B times y prime plus C times y equals the left-hand side I'll call f of t. Could be a function, could be 0 depending on the situation. And in this case, we're assuming here that A, B, and C are at least positive numbers. So if we think about the physical systems, we get to equations like this. We can abstract that into this sort of a system here. And these we know how to solve, at least for when the function on the right side is 0. We'll focus here on the case where this is 0 and deal with the other part later on. So our terminology that we use for these equations a lot of times comes from this mass on a spring system. So you think about the physical system, and the words used to describe that are related to the differential equation that models it. So if we go back to our model, which was A y double prime plus B y prime plus C y equals 0, or a function f of t, we say that the equation is unforced or free if the right-hand side is 0. That is, if the equation is homogeneous. Which basically comes from the idea that unforced means there's no extra forcing applied to it. There's no external forces outside of just the acceleration, the drag, and the spring constant. If there's no other forces, we say it's unforced or a free system. The B coefficient here relates to drag force, or how much the system is impacted by its external environment in terms of restricting the motion of this object. This is called the damping coefficient because it sort of dampens the oscillation of the movement by controlling how it can behave. If B is 0, we see the equation is undamped. Otherwise, we say it is a damped equation. We'll have different conditions on this damped equation that we'll see here in a second. So these words about being unforced or free equation or a forced equation, which is the opposite of that, comes from whether this equation is homogeneous or not. And we have the damping coefficient that is this B of this derivative term in the middle. Now, as long as this equation is homogeneous, we know how to solve it. If it's constant coefficient, it's second order, it's linear, it's homogeneous, we know how to solve all of those problems about them as we've discussed previously. So we can handle them. So we have our main equation, again, and there's different types of solutions you can get based on values of A, B, and C. So for instance, if we have B equals 0, this is our undamped equation. In that case, what do we get? Well, our equation is A y double prime plus C y equals 0. If A and C are both positive, these will turn into pure sine and cosine functions. So you'll end up with a C1 sine of omega t plus a C2 cosine of omega t. This is sort of a free oscillation, and this is the idea why these are called vibrations, because if we draw this out, right, this is a function that will just oscillate up and down forever, hence a vibration. Now what happens if B is a little bigger than 0 but not very much? Well, in that case, we'll have that B squared minus 4AC is less than 0, right? B is non-zero but small. This is called an underdamped equation. And the F for this is we're going to get complex solutions. So something like a c1 e to the minus lambda t cosine of ut plus same thing for sine. And this is the same idea, but they're going to decay in time. So it oscillates, but not periodically because it's going to decay to 0 in time. We have two more options here. We have if b squared minus 4ac equals 0. This is the critically damped case. In this case, our solution is the double root solution. So we're going to get a c1 e to the rt plus a c2 t e to the rt. And that gives us decay to 0, or potentially one oscillation and decay to 0. This does not oscillate. It just goes sort of straight to the equilibrium point, or passes through 0 once. And the last case is what we call overdamped. And this is when b is really big. So when I have b squared minus 4ac bigger than 0, I'm going to get two real roots. So in this case, I get sort of a c1 e to the r1t, c2 e to the r2t. r1, r2 are both negative here. So what I end up with is decay. Same sort of idea, either decay or one oscillation in decay. But in general, this decay is going to be slower than the critically damped case. There's all different words to talk about these solutions. We could talk about them being undamped, underdamped, critically damped, or overdamped based on these parameters. You get an idea for how these solutions behave based on these different properties. Important to know both what these words mean, how they relate to the equation, and how they relate to the different types of trajectory solution it can be on, given that it meets those different properties.